I'll continue today to talk about the general properties of remote sensing systems, the constraints that they impose on what we can know about the things that are being observed, as well as talking about actual ways that they've been implemented. On the other day, I covered spatial resolution and a little bit of spectral and radiometric resolution. So today I'll begin with temporal resolution. This property, really given in measured in time, is the time between observations made of the same location. It's related to the spatial coverage of a satellite or a sensor, generally related to the field of view. Larger field of view allows the same location to be observed by a sensor as it makes successive overpasses. Does not necessarily mean the time it takes for the satellite to revisit its previous location, just because the satellite can observe at a range of angles, and so can observe the same location at different angles through time. Or you can think the first overpass might be a little bit to the west of Montgomery, the next overpass a little bit to the east, so to speak. Some examples for the sensors, the MODIS sensors called the Moderate Resolution Imaging Spectroradiometer. That's a relatively high orbit multispectral and thermal sensor that is present on two different platforms. One that went up in the year 2000 called Terra, the other in the year 2002 called Aqua. And that sensor makes observations twice daily. Terra will make observations in kind of the late morning hours, and then 12 hours later, so I don't know, early night. Aqua makes an early afternoon observation, and then I guess very early morning, 3 a.m. or what have you. The spatial resolution of those sensors, so what is the pixel size, is for many bands 1,000 meters or a kilometer. There are some bands for which MODIS data are available at 500 meters or 250 meters, but it's generally what we call now a coarse resolution data product. It's kind of funny because MODIS is an acronym where the MOD come from moderate resolution. Kind of just an artifact of how things change in time. We looked at one figure from Chuvieco's book about how spaceborne satellite sensors generally became finer spatial resolution over the last few decades of the 20th century. So what was moderate resolution when these sensors were being designed in the 90s is now quite coarse. But of course, that's not to say that the data aren't useful. In fact, giving effectively daily observations, it either allows you to reliably track properties that can change on the scale of days, or it just gives you a lot more opportunities for high quality observations, say in tropical areas where cloud cover is kind of a persistent obstacle to having good observations of the rainforest or of any kind of development below the clouds. Having daily opportunities for data is very valuable. Contrast that daily observations from MODIS from the revisit period or temporal resolution of Landsat. This data, Landsat data, typically available at a 30-meter spatial resolution, so the pixel size, 30 meter by 30 meter. And those data are available for the same location every 16 days. So just to say one more thing about Landsat, 16 days every 2 weeks, it's typically what you think of as a good enough temporal resolution to monitor, say, deforestation or urban growth. I mean, in US, a lot of these construction projects take more than 2 weeks. And even in places like China, say, where you might see videos online of them putting up a skyscraper in a couple days, even in China, it's probably 16 days is what you'd expect to see to really capture a lot of the change as it's happening. The problem is again in those areas that I mentioned where cloud cover can be higher. And these could be areas that could also be times of year where clouds just seem to kind of settle in. Um, where if 16 days is, it's not a guaranteed new usable high quality image. It's just the next opportunity you have to have a good quality image. So Landsat data from the rainy season in the tropics can be a lot more rare in terms of usable data where you can see the surface of the Earth. So I'll move from a topic of resolution, which as we've seen talks about the kind of the finest grain, the finest degree to which a thing can be measured. For spatial resolution, we're talking about pixel size. For temporal resolution, how often are images available in best case. Now, coverage is also a term of use that can relate to both temporal and spatial dimensions of data. I just want to call attention to these because they mean different things in that they're referencing different objects. So for spatial coverage, that's similar to what we've learned is the field of view. Could be image bounds, spatial coverage of a sensor. In theory, you can imagine that it could also refer to the geographical limits of where a sensor is obtaining data. But in practice, it's not that often. It's in reference to the image, a data product coming from the sensor, not the sensor itself. We've seen with geostationary satellites that have an orbit that is in sync with the rotation of the Earth. Those sensors are always capturing data from the same location on Earth. Other sensors that have a polar orbit are not necessarily capturing data at all latitudes. There's one mission called the Tropical Rainfall Monitoring Mission. The acronym for that is TRIM or TRMM. And that only produces data between, I think, north 50 latitude and south 50 latitude. So it wouldn't have any data on polar precipitation. But when you hear spatial coverage, think of the coverage of an image or a sensor's field of view, what it can see at a moment. Temporal coverage, on the other hand, doesn't really refer to an image itself or a data product, but rather to the sensor. And as I mentioned with MODIS, you could have the same sensor model on different satellites. So I call that a sensor platform here. So temporal coverage is basically when did it go up and start sending back data, and when did it drop out of commission. So for something like Landsat 6, Landsat 6 doesn't have any temporal coverage because it never produced usable data. On the other hand, Landsat 5 was up from 1985 to 2012. I believe I got those dates right. Anyway, it was up for a long time, 27 years. So that's a mission that probably had a predicted lifespan of like 5 or 6 years. But if it wasn't broke, I'm not going to fix it. And so toward the end, they kind of had strategies for maximizing the fuel on board, optimizing data collection strategies. But all good things come to the end. But Landsat 5 in operation without major issue for over 25 years. Contrast that to Landsat 6, which never produced usable data, and Landsat 7, which by now has been operating for 20 plus years. But relatively early on in mission, there was an error that developed with the scan line corrector. And so those Landsat 7 images have the kind of characteristic tiger stripes or no data values affecting some of the pixel locations because of the design of the sensor and a malfunction of a part of them. So learning about these different types of resolution, really qualities of the sensor system that have implications for the quality of the data, there are a number of trade-offs. So this figure that I pulled from an open source paper kind of it shows the kind of change in field of view from unmanned aerial systems to manned systems to satellites. I mean, you can also imagine that there's difference between different satellite systems. Earlier in this slides, I contrasted MODIS with Landsat. And so you see kind of closer down, lower spatial coverage typically means finer spatial resolution. But on the other hand, the temporal resolution, or how often the same location is going to be observed by these different platforms, typically the length in days gets longer the smaller the spatial coverage. With things like drones and planes that aren't in orbit, that kind of clean and neat relationship breaks down a little bit. I mean, if you're totally unconstrained from all kind of costs, you could theoretically fly the drone every day or fly a different drone that has the same spec camera every day. So that kind of, when you're dealing with more than one sensor in a mission, what the term for that is a constellation when we think of the satellites. Maybe with UAS, you think of a term being a fleet. These trade-offs, they don't become false. They don't totally break down, but they become less constrictive. They define the relationship a little bit, or their relevance to an application decreases a little bit. And then finally, I'll revisit a figure I talked about in the last slides, highlighted it, what it was showing us about spectral and radiometric resolution. Just because I wanted to mention these again, because they also have a kind of what do you think of as a trade-off or a relationship with the spatial resolution of a sensor that generates these data. In this, we remember that the horizontal axis, kind of the length of these bands in spectral space, or the length of the wavelength of light that's being observed, can impact their kind of location, and their width can impact whether or not different materials are distinguishable from one another. And radiometric resolution being the degree of precision with which we can differentiate amounts of energy, of radiance really, on this vertical axis. So these two properties, spectral and radiometric resolution, are related to spatial resolution, and this kind of relationship is illustrated when we remember that radiance, the input energy that's being divided here by the total input energy from the sun, total that's reflected by the surface, is measured in watts, the energy, per meter squared per steradian. And the steradian, has to do with the angle of light. So that's a separate thing. But the meter squared has to do with the area. And so the size of the pixel will influence how much energy there is to be observed. So how much, I should say, reflected energy there is to be observed. It also has different implications for the amount of incident sunlight, and those get kind of divided out when you look at reflectance. But there is going to be a quantity of energy that the sensor is going to be observing. And the question is, with the sensor's radiometric resolution, how well can it detect difference in that energy? And so the amount of area that each observation is seeing, here the pixel size, as well as the width of the bin influences the amount of that energy. So if you're making one measurement, one band, over 0.3 micrometers, you're going to kind of have the sum energy over each of the three smaller bands, say, from 0.4 to 0.5, from 0.5 to 0.6, and so on. And the amount of energy, more in larger bands, in larger pixels, is going to influence how precisely you can measure the energy that's there, so the radiometric resolution. So this figure, I don't know, it has the right dimensions on these charts to illustrate it. I think the good examples that might help you understand it a little bit more are when you look at data from, say, Sentinel-2 or from Landsat-8 that has bands in the visible range, the near infrared, the thermal, and the data products from those sensors have different spatial resolution depending on the band. So for things like thermal energy, where there's just typically less energy to observe, those pixel sizes are generally larger because they need to be in order to get enough, to have enough energy over an area, so that's watts per meter squared, that the satellite sensor can be sensitive to. Another band that's within Landsat is called the panchromatic band. Not all the Landsat sensors have this, but it would be in the OLI, ETM+. And what panchromatic or all spectrum band is, it's looking not just at spectral albedo, but at all albedo. So of the energy that's in, regardless of wavelength, of all wavelengths, how much is leaving. And when you're measuring energy over all bands, panchromatic, there's just going to be more energy. And so you can actually detect differences over smaller areas. So if the red, the green, the blue wavelength Landsat reflectance data is distributed at 30 meters, the panchromatic data is distributed at a spatial resolution of 15 meters. So the pixel size is half the distance on end. And if you look at area, it's 1/4 of a typical Landsat 30-meter pixel.